Hello there. In this lesson, we're going to learn about the mole. The mole is a very central unit or quantity in chemistry, and all over North America and probably the world, in October, there is a little celebration of Mole Day, and they have little themes every year for different types of mole celebrations. And so we're going to learn a little bit about the mole today in this lesson, and hopefully you'll understand why Mole Day is significant and what the importance of the mole is to chemistry. So far in chemistry, you've learned lots about really big measurements, like you measure the volume of something, you determine the density, you measure the mass, and these give you quantitative and qualitative characteristics of different chemicals. And that's sort of one side of chemistry. And there's the other side of chemistry, which is the theoretical, where you learn how to bond atoms together and like electrons that are free to make these covalent bonds, and then reactions, and you know that you need two of these to react with one of these. And so this is all based on indirect evidence, and it's too tiny to be able to observe directly. So the mole is really important because it helps us to make a connection between these really tiny things, like the atoms in a compound that you can't see, or the proportions in a reaction that you can't really see as well, to something that you can measure, like volumes and masses. So we're going to use the mole to help us to understand really tiny things like particles in a compound or in a chemical reaction, and we're going to change that into measurable quantities that we can also follow in the lab, or we can use our measurements and use it to determine the amounts in a chemical reaction or the quantities in a compound. So that's where we're going with this, and so the mole is super useful for all that. So the mole concept is based on the idea of equivalent quantities, equal amounts of different particles. And you don't need to be able to measure the actual mass of a hydrogen or a helium or some tiny atom. All you need to do is have the relative mass of the two items. So let's use an example of stuff that we've seen every day. Let's say that we've measured a penny here, and we know that by putting them onto a balance that a nickel here has 2 times the mass of a penny. And so what you can do with that information is you don't need to actually know how much a penny actually weighs or a nickel actually weighs to be able to come up with equivalent quantities of pennies and nickels. All we need to know is that little bit of information about the relative mass of the two particles, of the two objects, right? So if we have a jar, and inside this jar is 3 kilograms of pennies, and we want to be able to have the exact same number of nickels. And we don't know how many pennies are in that jar. It's sealed shut, let's say. But what we can do, because we know the relative mass of them, because we know that a nickel is twice the mass of a penny, if we took the same amount of nickels, the same amount of nickels should have twice the mass, right? And so just like you know that an individual one is 2 times the mass of a single penny, well, 2 times the total mass will be the same number of nickels, equal number of nickels. So you don't have to know the exact quantities to be able to figure out equivalent quantities. We know that because of the relative mass of these two objects, that we have equivalent quantity of them because we have the same proportion of masses. So the same logic we use for the pennies and the nickels will work for atoms and molecules and compounds. If you know the relative mass, say I know that helium has 4 times the mass of a hydrogen atom. And I don't need to know how many there are, but knowing that information, I can always work out when I have an equivalent number, right? So if I have 5 grams of hydrogen in one balloon, if I want to put the same number of atoms into another balloon, only it's helium, and each helium is 4 times the mass of a hydrogen atom, well, I know that I got to multiply by 4, and it'll require 20 grams of helium to have the same number of particles. Same number of particles. And I use particles here because the helium are atoms, and the hydrogen comes in pairs, so these are molecules. So you use particles when you're just talking about the smallest bit of matter. So conveniently, everything on our periodic table, all the mass numbers on our periodic table, were measured relative to one another. The base unit they used was the carbon 12 isotope, and they designated that one being exactly 12 units. And then, using a mass spectrometer, you can see whether the isotopes are either heavier or lighter. And on the periodic table, looks like most of them are heavier. And so all these values, all these mass values on the periodic table, these average atomic masses, are all relative to the other atoms. And so what you can do is, because they're relative masses, we can do the same trick that we did with the atoms and the pennies earlier. You can take the number that you get in atomic mass units, just measure that in grams, that's measurable, and you'll know that you have the same number of atoms as, say, another element. There's lithium with roughly 7 grams. So 7 grams of lithium will have the same number of atoms as 32 grams of sulfur. It's just the sulfur atoms are larger. So that equivalent number of particles that matches the mass number on the periodic table, that is 1 mole of any element. So these mass values off the periodic table are now useful because they also represent the mass of a mole of particles, that base quantity of particles. So hydrogen is roughly a mass of 1 gram for a mole of particles. And if you have H2, that means you're going to have 2 atoms per particle. So if you had a mole of those particles, and each particle has 2 hydrogens in it, well, it's going to have a mass of 2 grams. And if you have a mole of water, and water has oxygen in it, oxygen has a mass of roughly 16, and also the 2 hydrogens, well, that's going to be 18 grams for a mole of water. So then it becomes easier to express this as a conversion unit. And so instead of saying 1 mole of water is 18 grams, you can say the molar mass of water is 18 grams per mole, grams for every mole. And you can do that for all sorts of compounds. All you need to do is just find the elements and add up the masses off of the periodic table. So for carbon, that's roughly 12. Oxygen is 16. 16 and 16, 32 plus 12, there's 44 grams in a mole. And it just a little more complicated for larger compounds, of course. So what do we have here? We have 2 aluminums, and aluminum has a mass of 27 grams per mole. And we've got 3 sulfurs, so 3 sulfurs, and each sulfur is 32 grams in a mole. And then we got 3 times 4, that's 12 oxygens, and each oxygen is 16 grams per mole. So we got to do a little multiplication and addition here, right? 2 times 27. Here, I'll pause it. So you can see that I just multiplied each one. So I got 2 aluminums makes 54, 3 sulfurs makes 96, 12 oxygens makes 192. Add them all up, and you get 342 grams per mole. So then if you want to convert between moles and mass, you can use those molar mass values. Carbon dioxide is 44 grams for every mole. And so if we want to know the mass of 15 moles of it, 15.5 moles, there's the big short form for moles, which is just to drop the E. What you do is you would multiply by the 44 grams in every 1 mole. And that would cancel out the moles, and you would end up with 15.5 times 44 equals 682 grams. And you can go the other way too. How many moles are in 130 grams of carbon dioxide? Well, moles equals 130 grams, and then we can use the 44 grams on the bottom for every 1 mole on the top. This time the grams cancel out, and you end up with moles. So 130 divided by 44 equals, look at that, 2.95, but then we got to round that up. So 95 so 3.0 moles. So there you go, moles representing equivalent quantities of particles. So eventually chemists worked out the actual number, the quantity of particles that was in a mole of any substance, and The number was named after Italian chemist who did a lot of studies using gases, and we'll discuss him a little later. But the quantity of the number of particles in a mole got his name put on it, I guess a few years after he died. And it's kind of cool because Avogadro is pretty close to avocado, and the number is the mole. And what do you make with avocados? Well, guacamole. Yeah, I always think that's cool. Okay, so the actual number is 6.02 followed by 21 more zeros. So if you move this decimal 23 spaces that way, that's the number of particles in 1 mole of anything, right? Mole of water, mole of hydrogen, mole of any substance. So now you know the origins of Mole Day. Mole Day is October, which is the 10th month, and the 23rd day, so that's the exponent from Avogadro's number there. And it's on a Sunday this year. But hopefully we can have some celebrations, or you can celebrate wherever you happen to be by doing something like make some guacamole or put a little mole on your face, or there's all sorts of funny stuff you can do just to acknowledge this really cool and important value for chemistry. I don't know if you saw the Mole movie that came out with Angelina Jolie, Maleficent. There's some pretty corny stuff out there. It's good stuff, good times. What kind of fruit did Avogadro eat this summer? Watermelons. All right, we'll see you soon.